Hi everybody, I'm Gauthier Tallec and I will be presenting SOS, which is a method for adversarial deep multitask learning using semantically orthogonal spaces. This is a work by Arnaud Dapogny, myself, Jules Bonnard, Edouard Yvinec, and Yvinec, and it is supported by both the French company Datakalab and the ISIR, which is the lab of Sorbonne University that is specialized in smart systems. So first, let's do a quick review about multitask learning. Basically, multitask learning regroups methods that aim at learning several tasks within a single architecture. This architecture will have parts that are shared across tasks and parts that are task-specific. Most of the time, what people do, and that is what is depicted on the slide, is they use a common encoder along with task-specific regressors for each task. In theory, there are several advantages for sharing parts across tasks. The most obvious advantage is computational cost reduction, as sharing operation reduces the total number of operations. A little less obvious is overfitting reduction. In fact, the idea is that using the same features as input to predict several tasks encourages the network toward producing more general features. This, in turn, will improve its generalization performance and reduce overfitting. However, in practice, the sweet spot that unlocks those advantages is pretty hard to get. In fact, it requires determining which part should be shared across tasks and which part should not be shared across tasks. Even worse, inappropriate sharing patterns, for example, sharing too much for unrelated tasks, may result in task loss competition in the shared parts, which may cause overall performance drops. In a nutshell, for classic multitask learning methods, the sharing pattern critically affects performance and is very difficult to set properly. To solve that problem, the objective of SOS is to avoid having to make that critical sharing pattern choice. For that purpose, it organizes task-related information by splitting it into a part that is common to all tasks and a part that is task-specific. To enforce this organization, it uses two types of auto-organization constraint. First, a soft auto-organization constraint, and second, an adversarial auto-organization constraint. But let's get into the technical details of SOS. So for a T-task problem, SOS projects encoders features into T+1 representation. So as I said before, there are T-task-specific representations and representation that is common to all the tasks, and the regressor for each task is simply a dense network that predicts using the representation of its task along with the common representation. So to organize the information flow, as I said before, SOS uses orthogonality constraints. So first, the soft orthogonality constraint. The aim of those constraints is to enforce complementarity between features by encouraging each task-specific features to be independent from both the common features. This is the first term, the first equation on the slide, and also to be independent from each other task-specific features. So this is the second equation on the slide. Then, the second type of constraints are adversarial constraint and is slightly more complicated to explain. In fact, we want each task-specific features to be necessary to predict the task it is designed for. Said otherwise, we want to prevent any regressors from being able to predict, say, task I with any other task-specific features than the one specific to task I. For that purpose, we simply train predictors to predict, say, task I from other specific features, for example, the feature specific to task K. So this gives us the first loss term on the slide, which is basically a classification loss that is optimized so that the predictor predicts task I from features specific to task K. Then, and that's where the adversarial magic happens, we train an encoder to make those very training difficult. So this is the second term, which is the opposite of the first term, but optimized only on the parameter theta of the encoder. Then, at the end of the training process, only task I specific features can be used to predict task I. And this is it for SOS global architecture. To generalize a bit the SOS architecture, we extended its principle to squeeze and excitation networks. So basically, we made a simple SOS-based quiz excitation layer. So that takes feature maps in input, squeeze it by predicting the task in a SOS fashion, and finally use those predictions to excite the different channels of the feature map. This architecture will be useful in the large-scale experiments. So first, from an experimental point of view, we started by testing SOS on 2 tasks toy experiments. So basically, there is 2 types of tasks in our toys. A type of task, that is to say whether a given point is on a donut, and a type of task, that is to say whether a point is on a sinusoid. The global idea is that by combining different instances of those tasks, we get situations in which tasks are related, for example, in the second row of a figure, and situations in which tasks are not related. So to investigate the behavior of SOS, we compared 3 different methods on both toys. The ST method, that is to learn the 2 tasks independently, the MT methods, which uses a shared backbone along with task-specific regressors, and finally, and obviously, SOS. We found out that whether tasks were related or not, SOS was always better than the 2 other methods, and that therefore, on those toys, SOS is a better multitask method. Finally, we tested our squeeze excitation version of SOS on the Celeba dataset, which is a large-scale multitask facial attribute detection dataset with 40 attributes. We compared SOS with other state-of-the-art methods and found out that it was a relatively handy architecture in 2 extents. First, it doesn't need to be pre-trained to work well, and second, it only requires few parameters to achieve good performance. So to summarize, I presented SOS, a new multitask learning architecture with efficient task-specific information storing using semantically orthogonal spaces. Experimentally, I have shown that SOS was better than other multitask baseline with a set of diverse toys. Finally, I showed that the squeeze excitation counterpart of SOS was a pretty handy architecture to use as it requires very few parameters with respect to other methods and can be trained from scratch. Thank you for your attention.